This is the software overview of the Vision Robot project. This is a replay of data from a run that was done earlier today where we successfully collected an object. So I thought it would be great to use for the explanation video. On the top left, what we're looking at is the main output window, and the green line here is what I refer to as the horizon line, and this separates the two subsystems of this software platform. Anything above it is obstacle avoidance, and anything below it is object detection. So those are the two main subsystems that are being developed. The obstacle avoidance on top is fairly easy and the oldest of the two that was developed. So what we're looking at here, for example, this line shows the high priority 1 obstacle as defined by the system, and it's saying we're going to keep an eye on this obstacle. We think this is the one we're going to collide with first of all if we keep going at the trajectory that we are, which in the beginning of the system should be just forward command. Because the horizon line is green, that means the threshold for worrying about the obstacles and actually performing a maneuver to avoid them has not occurred. That threshold is, we are well below that. When the threshold is breached, the line will turn red, and then we will actually see the robot make a motion in order to avoid the obstacle that's defined by this line. So for example, if it were to make a move to avoid this obstacle, that's what's written up here. The small value means the magnitude. It would slightly turn to the right. This is the direction to avoid this obstacle defined by this line. That's how that obstacle avoidance works. We're not going to see much of that in this example because it's a straight shot. As you can see, the object's already there. But here's the verbose output. One reason why I like to watch this is because the challenges of obstacle avoidance in the vision algorithm development is ensuring that all the actual obstacles that are present in the frame are being detected by the algorithm in order to establish that horizon line correctly. And conversely, any of the objects that are down here are not being detected by the algorithm, because what it would do is it would treat it as an obstacle to avoid, and the horizon line would jump down below the object that it believes is an obstacle. So that's the challenges in developing the obstacle avoidance algorithm. Basically, those are the two major ones. So object detection, anything below the horizon line, are these 6 images here. Each of these are an object detection algorithm unique unto itself, and they took years to develop, would warrant a very, very lengthy conversation that I just will not do. But just know that the combination of the output of these 6 algorithms and the state of the robot and the system prior, the frame process prior to that, is what determines what is an object, what is not an object, and then as time progresses, what the confidence level is of the object to perform a lock in order to move on it to collect. So right now in the beginning, you can see the status output here, these lines. This is actually the second frame. The first frame I used to come into this verbose mode where we see all the images. So the counters here, the horizon line, Y value, the previous point, the very first one was obviously 0 because it's the first one. And this is the detected point that came up for the object. This is the difference between the previous and the current one for the object. This is a poorly named variable called GotTemp. That just determines what state the software is in. 0 means object detection. We are looking for something that we can build a confidence up towards as a positive detection for an object. And then when it turns to 1, that means the confidence threshold's passed. We believe it's an object. We are going to then track / move on it / collect it. And this close CTR is part of that confidence counter that we're looking at. This output will change when we do move into the GotTemp 1, into object tracking, which we'll see here. But for right now, we'll just process through these frames so you can see the change of what's happening. So this very next frame, for example, because the object lock has, or the object detection has changed color from green to yellow, that means the method in which we are detecting the object and comparing these outputs versus the prior frame and this and that has changed, hence the color change. And you'll notice that this little image popped up because it's building its confidence. It has now taken a snapshot that's separate of the object for use later. And then as confidence builds, you'll see our counter increases and the system moves forward. Now the threshold is broke, we have changed, we've got a good confidence value here, and what's happening, it's clearest to see, is we've moved into the tracking mode because of this red line here. If you can have a sharp eye and tell that that's actually not in the middle of this image, and this is put in manually by me due to the hardware. When I built the robot, I'm not a mechanical engineer, so the middle of the lens of the camera is not perfectly in line with the center of the open gripper. So I had to line it up and actually set this number in as a static variable in the software system. This line represents where the middle of the gripper is located in the frame of the camera, because the camera is mounted on a tilt servo and will end up looking straight down at the ground in the object, and the gripper will be in the frame, and this needs to be in the center. It also represents and serves as the PID control set point. Well, I should say PD control because I'm not using the integral, but either way, this is also the goal for the robot to make motions to take this detected object and centerize it here on the x-axis, as well as a percentage value between the horizon and the bottom of the image, which, when the camera is fully tilted, is the gripper location, is the at the chassis of the robot. So those things are being tracked. Process the next frame so you can actually see the new image pop up, and then the magenta has signified that the basic summation of these 6 detection algorithms, which is this image, is what's providing the track, the lock. If this fails, because you'll see it fail, it will fail. The conditions of lighting and in real time, I mean, the camera's bouncing, it's not mounted well. The motors create vibrations in the chassis. There's frames that are blurry. There's this and that. If the object is not shown in this output image, we're not magenta, we'll try a secondary lock, which is using the image, the black and white image here, to match it as a template inside the frame, and then it'll turn white to a different detection method to keep that track alive, that lock alive for a frame or two until these algorithms come back online, so the robot can still perform its centering and its motion towards the object without just calling it a failure and lose the lock. And you'll see that happen. But also, our output has changed down here. We still have our counter, but now we have the output from our PID controller and our proportion of our object in the Y frame. This is the X and Y of the object used. This is the power and percentage of the left and right motor. Now we have our tilt, which is the tilt angle of the camera, and our GY, which is the Y value of where the grippers are located once we are at maximum tilt angle. These things, to explain them quickly, I have to just put these in from the logs. I take them from the logs and I paste them into the replay code because this is an actual thing that happened. But in real time, every time the robot starts, it actually tilts its camera by itself until it sees the gripper and then records that information. What is the maximum tilt value to command the servo? And then when the gripper is in frame, what is the Y value of that? Because, as you'll see, these detection algorithms are very sensitive. You can't have the gripper in the frame or else it'll throw these off. So it needs to know when it's already looking down and it sees the gripper where the gripper is, and then we'll see what happens once that occurs. So these are now the output of the text down here to kind of let you know what's going on with the system. So we'll watch it creep up on the object, and you'll notice that the horizon is getting low and the obstacles to avoid are getting fewer until it's none now. We're already tilted that much. And I think tilt max is 50 if you're looking at the text output on the bottom. But you'll see the noticeable change in the output image because we're going to have to black out the gripper in order to prevent the object detection algorithms from sensing it, which just occurred right now. We're at maximum tilt. We're pretty much centerized. We have blackout. The gripper would be visible right here. And in this first frame, it did fail. It caused a failure. These detection algorithms are not working. So we took this black and white image and we matched the template here in the frame in order so we can still provide data to our control methods to perform motions. Here's our next frame. It came back, lost it again, lost it. And now, because this message tilt max that object, what would have happened if it wasn't a replay of data is that the gripper will close itself on the object and then lift itself up and take pictures of this to show its progress as well as let me know how things are calibrated. So I saved this image here from the output logs. This was the last frame that was processed. This frame is raw. So as you can see, the middle line has now turned green, which is just, again, a little thing denoting that we're not running any code. We're just we're using this as a calibration test. And you can see the gripper now, and you can see how much the object has moved because we're looking at it slow frame by frame, but in real life there's momentum. The motors were moving at 20 and 19% at the time of this, so there's forward motion so that we're underneath the gripper claws themselves. And then you'll notice that the orientation of the object has changed a bit too. What ended up happening is it hit the right claw of the gripper and it's changing its orientation, which, as you'll see in this success, okay, but sometimes with some objects that creates a failure. It pushes it away or it causes it not to grip. And here is the lifted gripper after the collection event. And again, this centering line is exactly where I want it to be with the hardware. Unfortunately, there are accidents. They do collide with the wall or other objects and bolts come loose, and if things shift around and move around and bend, then I want to be able to see with this line that this line's in the, actually I could even go over a pixel or two probably, is down the center of the gripper when the camera's looking down at it in order to make sure that we know how to center that object for collection. And as you see, by the time it actually closed on it, it completely changed its orientation, by tens of degrees there for the collection, but it was successful. And that's basically the overview of the software system itself. We didn't cover the obstacle avoidance very much, but again, that's very boring. There's no recording, there's no mapping, there's no SLAM, there's no best route determining or any fancy thing like that. It's literally just processing frame by frame, saying if I'm close to an obstacle, which way do I turn and by how much so I can avoid it. Very simple. The object detection is really where it's at for this project. So as always, thank you for watching, and I hope you found this to be interesting.